Hi students, today I would like to deliver a lecture on thermal engineering subject. I am T. Nityanandam, Assistant Professor in the Department of Mechanical Engineering, M. Kumarasamy College of Engineering, Karur. The following contents are to be discussed in this delivery: the thermodynamic cycles, actual cycle and ideal cycle, assumptions for analysis of cycles, and Otto cycle, and the effect of compression ratio in Otto cycle performance, and the effect of specific heat ratio in the performance of Otto cycle. Generally, thermodynamic cycles, the two important area of application of thermodynamics are power generation and refrigeration. In power generation, the power output will be obtained, and in refrigeration we will be getting cooling effect or heating effect. Both are usually accomplished by the systems that operate on a thermodynamic cycles. The thermodynamic cycles can be divided into two categories. One is called power cycle and another one is called refrigeration cycle. The power cycle produces power and the refrigeration cycle produces heating effect or cooling effect, generally called as refrigeration effect. The devices or systems which are used to produce the net power output are called engines. Under the thermodynamic cycles, they operate on are called power cycles. Here, the engines are operating under the power cycles. The devices or systems used to produce a refrigerating effect are called refrigerators or air conditioners or heat pumps. And the cycles they operate on are called refrigeration cycles. In refrigerator and the air conditioner and heat pump, in which the refrigerator produces cooling effect, air conditioner which produces cooling effect and maintaining the effect for the whole system, and the heat pump which produces the heating effect. The thermodynamic cycles can also be categorized as a gas cycles and vapor cycles depending on the phase of the working fluid. In gas cycles, the working fluid remains in the gaseous phase throughout the entire cycle, and in vapor cycles, the working fluid exists in the vapor phase during one part of the cycle and in the liquid phase during the another part. In the thermodynamic cycles can be categorized in another way: closed and open cycles. In closed cycles, the working fluid is returned to the initial state at the end of the cycle and is recirculated. But in open cycles, the working fluid is renewed at the end of each cycle instead of being recirculated. And based on this, we can classify the gas cycle into different ways. One is Otto cycle, diesel cycle, dual cycle, Lenoir cycle, Stirling cycle, and etc. The vapor cycle can be classified into different ways: Rankine cycle and Joule cycle. In actual and ideal cycle, the cycles encountered in actual devices which are very difficult to analyze because of the presence of complicating effects such as friction and the absence of sufficient time for the establishment of the equilibrium conditions during the cycle. To make an analytical study of the cycle feasible, we have to keep the complexities at a manageable level and utilize some idealizations. Otherwise, the analysis of the cycle will be very difficult and it will be complicated. When the actual cycle is stripped of all the internal irreversibilities, the irreversibilities which are nothing but friction and the complexities, we end up with a cycle that resembles the actual cycle closely but is made up of totally internal reversible processes. Such a cycle is called ideal cycle, which means the ideal cycle we have eliminated the frictions. So these are all the irreversibilities and we have made the irreversibilities negligible, and we will consider the reversible processes only, so that the cycle is called ideal cycle. A simple idealized model enables engineers to study the effects of the major parameters that dominate the cycle without getting bogged down in the details. The conclusions reached from the analysis of ideal cycles are also applicable to the actual cycles. The actual gas power cycles are rather complex. We already discussed. To reduce the analysis to the manageable level, we utilize the following approximations, commonly known as the air standard assumptions. The working fluid of air is air, which continuously circulates the closed loop and always behaves as an ideal gas. So in which we have to consider the working fluid is air, and it should behave as an ideal gas, so that only we can compare all the cycles. And second, all the processes that make up the cycle are internally reversible. As we discussed, if the cycle is having lot of irreversibilities such as friction and complexity, if we consider those irreversibilities, it is very difficult to compare the cycles for the same parameters, so that all the processes that make up the cycle are internally reversible. The combustion process is replaced by a heat addition process from an external source. Here we are not doing any actual combustion, which is like engines. For the feasibility of the analysis, the heat addition process can be done by some external source. The exhaust process is replaced by heat rejection process that restores the working fluid to its initial state, so that the process will be recycled. The air has constant specific heats whose values are determined at room temperature, but actually the specific heat will be varied based on the temperature. It is a function of temperature, but for the analysis we have to consider the specific heat will be constant at room temperature. These are all the assumptions to derive the efficiency of an thermodynamic cycle, and it will be possible to compare the cycle with another cycles. And here we are going to see an overview of reciprocating engines. Despite its simplicity, the reciprocating engine, basically a piston cylinder arrangement, is one of the rare inventions that has proved to be very versatile and to have a wide range of applications. It is a powerhouse of vast majority of automobiles, trucks, light aircrafts, ships, and electric power generations, as well as many other devices. Here we could able to see the piston cylinder arrangement, in which we can see the some specifications and components. One is bore. It is the diameter of the piston or cylinder, and the stroke, it is the distance between the top dead center and bottom dead center, and the inlet valve, which allows the air fuel mixture into the combustion chamber, and exhaust valve, which allows the exhaust gases from the engine cylinder to the atmosphere. And we should know about top dead center. Top dead center, which is nothing but when the piston which is at the top dead center, which produces minimum volume in the combustion chamber. Then bottom dead center, it is the position of piston which produces maximum volume in the combustion chamber. The stroke volume is the distance between the volume occupied between top dead center and bottom dead center. And clearance volume, which is the minimum volume in the combustion chamber when the piston reaches the top dead center. These are all some specifications of the engine cylinder, piston cylinder arrangement. Now the SI and CI engine, SI is nothing but spark ignition engine and CI engine is compression ignition engines. These engines, these reciprocating engines, depending on how the combustion process in the cylinder is initiated. In SI engines, the combustion of the air fuel mixture is initiated by the spark plug. In CI engines, the air fuel mixture is self-ignited as a result of compressing the mixture above its self-ignition temperature. That is why it is called as compression ignition engine. Because of the compression process, the burning is happening. So that is why compression ignition engine. In spark ignition engine, we have to create a spark by spark plug so that the air fuel mixture is started burning. There are many thermodynamic cycles present, such as Otto cycle, Diesel cycle, Joule cycle, Lenoir cycle, Stirling cycle, Duell cycle. Here in my lecture, I would like to deliver about Otto cycle. The Otto cycle is the ideal cycle for spark ignition reciprocating engines. It is named after Nicholas A. Otto, who built a successful 4-stroke engine in 1876 in Germany using the cycle proposed by the Frenchman Beau de Ricos in 1862. In most spark ignition engines, the piston executes 4 complete strokes, which consist of 2 mechanical cycles within the cylinder, and the crankshaft completes 2 revolutions for each thermodynamic cycles. These engines are called 4-stroke internal combustion engines. Here we could able to see the actual and ideal cycle for 4-stroke Otto cycle. The first image represents the PV diagram for Otto cycle, which is actual cycle. The second PV diagram represents the PV diagram of ideal cycle. Here in Otto cycle, there are 4 strokes will be processed. First stroke is called compression stroke, power stroke, followed by exhaust stroke and intake stroke. In compression stroke, the air fuel mixture already which is available in the combustion chamber will be compressed to high pressure so that the temperature and the pressure are increased. During this compression stroke, the valves, both the valves will be closed. And power stroke. In power stroke, the highly compressed air fuel mixture will be ignited by the spark plug. This spark plug which creates spark and it ignites the air fuel mixture. This ignition which produces very high pressure and temperature. This high pressure and temperature burnt gases pushes the piston towards down so that the piston is moving from top dead center to the bottom dead center. During this expansion stroke, the power output will be obtained from the piston and this power is transmitted to the connecting rod to the crankshaft so that the useful power available at the crankshaft. And in exhaust stroke, the exhaust valve is opened. So during this stroke, the burnt gases after power transmission will be exited to the atmosphere through the exhaust valve. And during this stroke, the piston is moving from bottom dead center to the top dead center. And in next stroke is called intake stroke. During this intake stroke, the inlet valve is being opened and exhaust valve is closed. So now the piston is started moving from top dead center to the bottom dead center. So the fresh air fuel mixture will be inducted into the combustion chamber during this stroke. Then the next stroke is again compression stroke. So in compression stroke, the piston is moving from bottom dead center to the top dead center, during which the sucked air fuel mixture will be compressed. So this is continuously taking place to produce power in the power stroke. But in ideal cycle, the same process will be happened, but the heat addition will be taking place by adding a heat source during the at the end of the compression stroke, so that the power is produced and heat is supplied. But in intake stroke, heat rejection is taking place by bringing a cold object which will be kept on the cylinder head, so that the heat is rejected from the engine cylinder to the out. So here heat addition and heat rejection is taking place by bringing the hot and cold object on the cylinder head. But the working fluid in the ideal cycle is air. So here air plus fuel mixture is not considered, only air is the working medium as we discussed in the assumptions, so that it will be easy to compare all the thermodynamic cycle performance. Here we could able to see the PV diagram of actual and ideal cycle of Otto cycle. So we can see the processes one by one. And now we are going to see the working principle of spark ignition engine of two-stroke cycle. In two-stroke, the piston has to move up and down for a single power cycle. Here instead of valve, we will have ports. There are 3 ports available in the two-stroke engine. One is called intake port and exhaust port and transfer port. In exhaust port, the exhaust gases will be sent to the atmosphere. In intake port, the air fuel mixture will be supplied into the combustion chamber. And when the piston will be moved from top dead center to the bottom dead center, so the intake port supplies air fuel mixture to the top of the piston. So this is called downward stroke. When the piston has to move from upward stroke, which means the compression and power stroke will be happening. So this is the two strokes. So in two strokes, one power stroke will be obtained. And next we will see the analysis of Otto cycle. So as we discussed, the following assumptions we have made, so that the thermodynamic analysis of actual 4-stroke or 2-stroke cycles described is not a simple task. However, the analysis can be simplified significantly if the air stand assumptions are utilized. The resulting cycle, which closely resembles the actual operating conditions, is the ideal Otto cycle. It consists of 4 internally reversible processes, because we have eliminated all the irreversibilities. Then only it is easy to compare thermodynamic cycles. The process 1 to 2 is isentropic compression process. The process 2 to 3 is constant volume heat addition process. 3 to 4 is isentropic expansion process, and 4 to 1 is constant volume heat rejection process. Yes, this is the pressure, volume and temperature entropy diagram of Otto cycle. Here we could see two processes, 1 to 4 and 2 to 3 are the constant volume processes, and 1 to 2 and 3 to 4 are the isentropic processes. Why we are calling the 1 to 2 and 3 to 4 processes are isentropic processes? Because the irreversibilities are eliminated, so that it is reversible adiabatic process. And in compression stroke, the process 1 to 2, the air is compressed isentropically. So during this process, entropy is constant, which can be represented in temperature entropy diagram. We could see the process 1 to 2 is isentropic compression process. During this process, the temperature and the pressure is increased and the volume is getting decreased. And process 2 to 3, the air is heated by bringing the hot object into the cylinder head to heat the air. So the heat is supplied to the air, which can be represented in TS diagram. Here the temperature is raised significantly and the pressure is raised enormously. During this process, the volume is kept constant. And 3 to 4 is isentropic expansion process. During this process, the power is obtained from the combustion chamber by burning the air. That means heat adding to the air, so that we will get power output. The expansion process is taking place. The process is reversible adiabatic process, which can be represented in TS diagram. We could see 3 to 4 is the reversible adiabatic or isentropic process, where the entropy is constant. S3 is equal to S4. And 4 to 1 is constant volume heat rejection process. During this process, the heat is rejected from the combustion chamber to the atmosphere by bringing cold object to the cylinder head, so the heat will be removed. So this process is happening at constant volume. So this process is called constant volume heat rejection process. So again the point 1 is reached. It is an thermodynamic cycle. Now we could see the air standard efficiency of the Otto cycle, so which can be derived here, in which we have to consider 1 kilogram of working substance, which is nothing but air in the ideal cycle. So the amount of heat supplied at constant volume process equal to mass into specific heat capacity at constant volume into temperature difference between that heat addition process. So the heat addition is represented process 2 to 3, so that the temperature difference is T3 minus T2, and heat rejected at constant volume process equal to mass into specific heat capacity at constant volume into temperature difference between the heat rejection process. The temperature difference is T4 minus T1. Here the mass is not represented here, because we have considered the mass is 1 kilogram. And now we will be able to calculate work done. So work done equal to the amount of heat supplied minus heat rejected, as we see in the thermodynamics second law. So the heat supplied is Cv into T3 minus T2 minus heat rejected is Cv into T4 minus T1. Now we could see the efficiency of Otto cycle. So work efficiency is equal to net work output divided by heat supplied. Work done is heat supplied minus heat rejected, and heat supplied is Cv into T3 minus T2. If we simplify this equation, we will get efficiency equal to 1 minus T4 minus T1 by T3 minus T2. Now we have to reform this equation based on the compression ratio. Before that, we have to define the compression ratio. Compression ratio is represented RC generally we will take R equal to V1 by V2. So V1 is the total volume of the cylinder. V2 is the clearance volume of the cylinder. So we can define the compression ratio is the ratio between total volume and clearance volume. And now we have to see about expansion ratio. Expansion ratio is represented as R suffix E. So here we will be taking equal to R, which is nothing but the point V4 and V3. V4 is nothing but the volume after expansion process. V3 is the clearance volume. So the definition is, for expansion ratio, it is the ratio between the volume after expansion and before expansion. These two ratios are same in this cycle because V1 is equal to V4, V2 is equal to V3. So that these ratios are equal. So compression ratio is equal to expansion ratio in the Otto cycle. So that we commonly take it as R. And now we have to see the relationship between temperature and volume for the process 1 to 2. The process 1 to 2 is the isentropic compression process, in which temperature volume relation will be T2 by T1 equal to V1 by V2 power gamma minus 1. Now from this equation we have to find out T2. So T2 will be equal to, T1 will be moved to the right hand side. So T1 into V1 by V2 is nothing but R. So R power gamma minus 1. So finally T2 is equal to T1 into R power gamma minus 1. Similarly, we have to write the equation temperature and volume relationship for the expansion process. So from the point T2 3 to 4, we can write this equation, and T3 by T4 equal to V4 by V3 power gamma minus 1. So from this equation we will be able to find out T3 is equal to T4 into R power gamma minus 1. So in this case we moved T4 in the right hand side. And now we have to substitute T2 and T3 in the equation. We will get efficiency of Otto cycle equal to 1 minus T4 minus T1 divided by, instead of T2, instead of T3, we have to substitute these terms, and finally we will get 1 minus 1 divided by R power gamma minus 1. R is the compression ratio, gamma is the adiabatic index. So R the specific heat ratio, so which is nothing but specific heat at constant pressure by specific heat at constant volume, that is equal to gamma. So the gamma value for air is equal to 1.4. Now the thermal efficiency of the Otto cycle depends on the compression ratio of the engine and specific heat ratio of the working fluid. So the thermal efficiency of ideal Otto cycle increases with both compression ratio and specific heat ratio. So this is also true for actual spark internal combustion engines, spark ignition internal combustion engines. For a given compression ratio, the thermal efficiency of an actual spark ignition engine is lesser than the ideal Otto cycle because of the irreversibilities such as friction and other factors such as incomplete combustion. These two factors will reduce the efficiency of the spark ignition engine when the process is actual. And now we have to see the effect of compression ratio in the efficiency of the Otto cycle. The efficiency of Otto cycle, as already derived, 1 minus 1 divided by R power gamma minus 1. R is the compression ratio, gamma is the specific heat ratio. Now we have to change the value of R. From first equation we could see the efficiency of 49.5% we have obtained for the compression ratio. R is equal to 5.5. And in the next equation the compression ratio is changed to 6, now we could able to see the efficiency of the Otto cycle, which is 51.16%. And now we have raised the compression ratio to 6.9. The efficiency is derived as 53.8%. And now another compression ratio such as 8, for this compression ratio the efficiency of the Otto cycle is 56.5%. From these values we could understand when the efficiency is increased while increasing the compression ratio. So which can be represented clearly in the graph, in which when the compression ratio increases we could see the curve, the efficiency of the Otto cycle increases. When the compression ratio is at low, the efficiency curve will be very steep. At lower compression ratio, the rate of increasing efficiency will be higher. When the compression ratio is higher, the efficiency of increasing rate will be little lower. For gasoline engines, for spark ignition engine, a typical compression ratio value is generally from 7 to 10. And now we would like to see the effect of compression ratio while increasing the efficiency of the Otto cycle. The thermal efficiency curve is rather steep at a low compression ratio, but flattens out starting with the compression ratio value of about 8. From this, the increase in thermal efficiency with the compression ratio is not as pronounced at high compression ratios. Also, when the high compression ratios are used, the temperature of the air fuel mixture rises above the auto ignition temperature of the fuel. From this point we could understand when we raise the compression ratio, the temperature of the air fuel mixture rises. When the temperature of the air fuel mixture rises, the burning of fuel will be happened earlier. So in the third point we could see the causes an early and rapid burn of the fuel at some point or points ahead of the flame front, followed by almost instantaneous inflammation of the end gas. This premature ignition of the fuel, called auto ignition, produces an audible noise which is called engine knock. So this is called knocking. The auto ignition in spark ignition engine cannot be tolerated because it hurts performance and can cause engine damage. The requirement that auto ignition not be allowed places an upper limit on the compression ratios that can be used in the spark ignition internal combustion engines. The improvement of the thermal efficiency of gasoline engines by utilizing higher compression ratio up to about 12 without facing the auto ignition problem has been made possible by using gasoline blends that have good anti-knock characteristics, such as gasoline mixed with tetraethyl lead. From these 2 points we could understand when we increase the compression ratio, which produces the unnecessary sound, so that which is called knocking. This knocking which can damage the engine and engine performance, so that we are unable to increase the compression ratio of the gasoline engines, which produce unnecessary happenings. But we can improve the thermal efficiency of the gasoline engines by increasing the compression ratio without facing any problem, so that we have to use some additives which can be mixed with the gasoline, which will help the compression ratio to be higher without any knocking process. Tetraethyl lead had been added to the gasoline since 1920s because it is an inexpensive method of raising the octane rating, which reduces the knocking, which is a measure of the engine knock resistance of a fuel. Leaded gasoline, however, has a very undesirable side effect. It forms compounds during the combustion process that are hazardous to the health and pollute the environment. So that it has been produced unnecessary effects which pollute the atmosphere and which are hazardous to the health, so that it has to be stopped in later years. So most cars made since 1975 have been designed to use unleaded gasoline, and that the compression ratio has to be lowered to avoid the engine knock. The readily available high octane fuels made it possible to raise the compression ratios again in the recent years. And now we have to see the effect of specific heat ratio. The second parameter which are affecting the thermal efficiency of an ideal Otto cycle is the specific heat ratio. Specific heat ratio is nothing but the ratio between specific heat capacities at constant pressure and constant volume. For a given compression ratio, the ideal Otto cycle using monoatomic gases such as argon or helium, where the specific heat ratio is 1.667, as the working fluid will have the high thermal efficiency. The specific heat ratio K or gamma, thus the thermal efficiency of an Otto cycle decreases as the molecules of the working fluid gets larger. The working fluid in actual engines contains larger molecules such as carbon dioxide, and the specific heat ratio decreases with temperature, which is one of the reasons that the actual cycles having lower thermal efficiencies than the Otto cycle. So from this point of understanding, when we using the higher specific heat ratio, the molecules will be decreases the molecules of the working fluid gets larger, so that the thermal efficiency is getting reduced. Now we would like to see some numerical problems in Otto cycle, in which I have given one example. The efficiency of the Otto cycle is 60% and specific heat ratio is 1.5. What is the compression ratio? From this we could see that the efficiency of the Otto cycle is 60%, ratio of specific heat is 1.5, and the compression ratio are to be asked. So we know that the well-known formula, Otto cycle efficiency is equal to 1 minus 1 divided by R power gamma minus 1. Here in this problem, Otto cycle efficiency is available 60%. Here it is noted as 0.6 will be equal to 1 minus 1 divided by compression ratio. We are going to find out the compression ratio. For the specific heat ratio is 1.5. So with these parameters we will be able to find out the compression ratio. So in this problem the compression ratio is found 6.25 for the efficiency is 60% and the specific heat ratio is 1.5. And now we will see one more numerical problem in Otto cycle. An engine of 250 mm bore and 375 mm stroke works on Otto cycle. The clearance volume is 0.00263 meter cube. The initial pressure and temperature are 1 bar and 50 degrees Celsius. If the maximum pressure is limited to 25 bar, find the following: the air standard efficiency of the cycle. For this understanding, we should draw the PV diagram of Otto cycle, in which V1 is the total volume, Vs is the stroke volume, Vc is the clearance volume. The maximum pressure is 25 bar. So in this problem, diameter of the engine is given D equal to 250 mm, which can be converted into meter, and stroke is L equal to 375 mm, and which is equal to 0.375 meter, and clearance volume Vc equal to 0.00263 meter cube, and initial pressure is represented as P1, with the compression process starts from point 1 and it ends at point 2. So the initial pressure is P1 equal to 1 bar, and initial temperature T1 equal to 50 degree Celsius, which can be converted into Kelvin. We are going to calculate for absolute temperature value. And maximum pressure in this PV diagram can be represented as P3, which is equal to 25 bar. The value is given. And now we are going to find out the swept volume or stroke volume equal to pi by 4 into d squared into L. So d is available and L is given. So from this we could able to find out stroke volume. Stroke volume is 0.0184 meter cube. And from this value we are going to calculate the compression ratio. To find out compression ratio, we need stroke volume and clearance volume. Stroke volume just before we found, and the clearance volume is available in the given data. So that compression ratio is equal to stroke volume plus clearance volume by stroke volume. Stroke volume plus clearance volume is nothing but total volume of the cylinder. So from this given data, the compression ratio is found 8. From this compression ratio, we are going to calculate the air standard efficiency of the Otto cycle. So the efficiency of Otto cycle equal to 1 minus 1 divided by R power gamma minus 1. So we have already derived this equation. So from this, if we substitute compression ratio in this equation, we found the efficiency of the Otto cycle is 56.5%. And we can see one more problem in Otto cycle. The minimum pressure and the temperature in an Otto cycle are 100 kilopascal and 27 degrees Celsius. The amount of heat added to the air per cycle is 1500 kilojoules per kilogram. So that from this given data, we are going to find out pressure and the temperature of all the points of the air standard Otto cycle, and we are going to calculate the specific work and the thermal efficiency of the cycle for a compression ratio of 8:1. And in this problem, we have to assume the CV value is equal to 0.78 kilojoules per kilogram Kelvin and specific heat ratio is 1.4. From this problem, we will be able to write the given data. The pressure P1, because it is the minimum pressure, P1 equal to 100 kilopascal, and T1 minimum temperature in the cycle is T1. T1 equal to 27 degrees Celsius can be converted into absolute temperature scale, and heat added 1500 kilojoules per kilogram during the process 2 to 3, and the compression ratio is given as 8, and specific heat capacity at constant volume is 0.72 kilojoules per kilogram Kelvin, and gamma specific heat ratio is equal to 1.4. So here in this problem, we have to consider the mass of air is equal to 1 kilogram is consumed inside the cylinder. Now the first step, we have to find out the pressures and the temperatures at all the points. So during this process 1 to 2, we have to use the relationship temperature and volume. From this equation, we could find that temperature at the end of compression T2 is equal to 689.1 Kelvin. And for the process 1 to 2, we will write pressure volume relation, P2 by P1 equal to V1 by V2 power gamma. So this is isentropic compression process. So from this relation, we could be able to find out P2, which is equal to 18.379 bar. All other terms are known value. And from the process 2 to 3, the heat added is available 1500 kilojoules per kilogram. So we know the heat added formula, mass into specific heat at constant volume into T3 minus T2, which is equal to 1500. So that from this process, CV is available in the data, and T3 is unknown value, T2 just before we found out, so 1500, which from this equation we will be able to find out T3. So T3 will be 2772.4 Kelvin. And now we are going to find out P3. So we can take the process 2 to 3, which is constant volume process. For constant volume process, the pressure and the temperature relationship will be like this: P2 by T2 equal to P3 by T3, because the volume is constant, so that V2 and V3 will be eliminated. So P3 is equal to 73.94 bar from this equation. This is the maximum pressure in this problem. And from this equation, the temperature volume relation has been written for for the process 3 and 4, which is reversible adiabatic expansion process. So from this equation we could able to find out T4. All other values are known, so that T4 is equal to 1206.9 Kelvin. And from process 3 to 4, it is, we could be able to find out P4 from this process. So P4 is equal to 4.023 bar. So now we found all the pressures and the temperature values for all the points 1, 2, 3 and 4. And now we are going to find out specific work. So which is nothing but heat added minus heat rejected. So as we discussed in the derivation, heat added is equal to Cv into T3 minus T2, and heat rejected is Cv into T4 minus T2. So now we have to substitute all the temperature values and the specific heat values. We will be able to find out the specific work is equal to 847 kilojoules per kilogram. And finally we have to find out thermal efficiency is equal to 1 minus 1 divided by R power gamma minus 1. So in this problem the compression ratio for the Otto cycle is given as 8 and the specific heat ratio is 1.4. So we could be able to find out the thermal efficiency. So thermal efficiency of this cycle is 56.47%. I hope this lecture will make you to get some idea about Otto cycle, and we have solved a few numerical problems for the sake of understanding. Thank you very much.